In this lesson, you will learn how to sketch curves. This lesson was recorded in two parts because of the length of each problem. So when you sketch a curve, you want to start with the function f of x, and in the function you want to look for the domain, the x-intercepts, and the x-intercepts are found by setting y equal to 0. Next you want to find the y-intercept, which is found by setting x equal to 0. And then together you want to look for any vertical asymptotes or holes, also called deleted points. So as an example, if you had the function y equals x plus 3 over x squared minus 9, you would take this function and factor to the denominator, and since the x plus 3's cancel, the function can be rewritten as 1 over x minus 3. So the hole occurs where you have a canceled factor. So the x plus 3 set equal to 0 is x equals negative 3. To find the y-coordinate of the hole, you take 1 over negative 3 minus 3, which is 1 over negative 6, so that the coordinate of the hole is negative 3, negative 1/6. To find the vertical asymptote, you take the factor that doesn't cancel, which is the x minus 3, and set it equal to 0. So the equation of the vertical asymptote is x equals 3. Next you want to find horizontal asymptote and slant, also called oblique asymptotes. And when you're looking for horizontal asymptote, you want to look for the degree of the numerator compared to the degree of the denominator. It can either be greater than, less than, or equal to. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the equation of the horizontal asymptote is y equals the ratio of the leading coefficients. To find the slant or oblique asymptote, this occurs when you have no horizontal asymptote, which is when the degree of the numerator is greater than the degree of the denominator. So to find the equation of the slant asymptote, you use long division. So once you've checked all of these items, then you go to the first derivative and you find the domain, the critical points, and determine if those critical points are maximum or minimum points, and then the intervals where the graph is increasing and or decreasing. Next, you want to find the second derivative, and using the second derivative you want to find any inflection points and determine the intervals where the graph is concave up and or concave down. So now let's go to example 1. And the directions are to sketch the graph of each function, and we will use the checklist above. So the first thing I'm going to do is look at the function f of x, and I first want to find the domain. And to find the domain, since I have a fraction, the denominator of a fraction cannot equal 0, so I take x squared minus 1 and I set it equal to 0. And when I take the square root of both sides, I get x cannot equal plus or minus 1. So after I find the domain, I now look for the x-intercepts, and the x-intercepts are found by setting y equal to 0. So I take 0 equals 2x over x squared minus 1, and I cross multiply so that x equals 0. And then if I substitute 0 into the function, I also get 0, so that the equation of the x-intercept is 0, 0. So since the equation of the x-intercept is 0, 0, that means that the y-intercept will also be the origin, so it has the same point, 0, 0. And after I find the y-intercept, I now want to look for any vertical asymptotes and or holes on this graph. So if I write the original function, y equals 2x over x squared minus 1, and if I factor the denominator, the numerator doesn't factor, and since nothing cancels, that means that there are no holes in this graph. So I just take the two factors in the denominator, x plus 1, set it equal to 0, and x minus 1, set it equal to 0, and I get x equals negative 1 and x equals positive 1. So the equations of the vertical asymptotes are x equals plus or minus 1. Next, I look to see if there is a horizontal asymptote or a slant asymptote. And to determine if it has a slant asymptote or a horizontal asymptote, I look at the degree of the numerator and compare it to the degree of the denominator. The degree of the numerator is equal to 1, and the degree of the denominator is equal to 2. So since the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the equation y equals 0, and since it can't have both a horizontal and a slant asymptote, the slant asymptote is none. So everything that we found with the original function, I'm going to take and place it on this graph. So I have an x-intercept of 0, 0. Then I have vertical asymptotes at x equals negative 1 and x equals positive 1. And the last thing I have is a horizontal asymptote at y equals 0. And since 0, 0 is an intercept, it means that this graph will touch the horizontal asymptote. Graphs can touch horizontal asymptotes, but they can't touch vertical asymptotes because vertical asymptotes are not in the function's domain. Now that I'm finished with f of x, now I move on to the first derivative. So to find the first derivative, I have to use the quotient rule. Now that I'm finished with the function, now I move on to find the first derivative. And to find the first derivative, I have to use the quotient rule. So I take the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator and divide it by the denominator squared. And if I distribute the 2, I can rewrite this as negative 2x squared minus 2 over x squared minus 1 squared. And I start by finding the domain. And the domain of the derivative is the same as the domain of the function. The denominator cannot equal 0, so therefore x squared minus 1 cannot equal 0. And if we solve for x, x cannot equal plus or minus 1. And we already know from the function that plus or minus 1 were vertical asymptotes. So now, to find the critical points, I take the numerator, negative 2x squared minus 2, and set it equal to 0. And if I add the 2 to the right, I have negative 2x squared equals 2. And when I divide this by negative 2, I have x squared equals negative 1. So when I take the square root of both sides, I get x is equal to plus or minus I. So this means that there are no critical points. So if there are no critical points, I still want to make a number line with the points that are not in the domain, which is negative 1 and 1, and I want to pick points within each of the 3 intervals and substitute them into the first derivative to determine if the function is increasing or decreasing in between the vertical asymptotes. So I will take f prime of negative 2 and then f prime of 0 and f prime of 2 And now I will take the 3 points and substitute them into the first derivative, And we are not looking for the value, but rather we are looking to see if the answer is positive or negative, so that we know whether or not the function is increasing or decreasing. So when I take negative 2 and substitute it in for x in the first derivative, I end up with something negative in the numerator and something positive in the denominator, which means the answer will be negative So I want to take these 3 points and substitute them in the first derivative, and if you'd like, you can factor the first derivative out of negative 2 and write this as x squared plus 1 over x squared minus 1 squared. And for each of these 3 points, you will see that you will have a negative 2 on top times a positive value inside parentheses, and then over a positive value in the denominator. So the answer will be negative, which means that it will be decreasing to the left of negative 1. And then for 0, I will have a negative times a positive over a positive. So once again, this will be negative, and the graph will be decreasing. And then for f prime of 2, I will have a negative times a positive over a positive. So this entire graph will be decreasing. And now that we've used found everything that has to do with the first derivative, now we use the second derivative to find any inflection points and the intervals where the graph is concave up and concave down. So now that we've found everything that has to do with the first derivative, now we find the second derivative to find the inflection points and the intervals where the graph is concave up and concave down. So for the second derivative, I need the quotient rule again. So now that I've found everything that has to do with the first derivative, now I find the second derivative so I can find any inflection points and the intervals where this graph is concave up and concave down. So I take the second derivative using the quotient rule, and I simplify the numerator. And one thing I notice is that I have an x squared minus 1 in all three terms, so I can cancel an x squared minus 1 and distribute that negative 4x and if I take 2 times 2x, I will distribute that 4x to the negative 2x squared minus 2. So that the second derivative simplifies to 4x to the third plus 12x over x squared minus 1 to the third. And to find the inflection points, I take the numerator and set it equal to 0. And I factor out a 4x and I get x equals 0. And then when I take x squared and subtract the 3 from both sides and take the square root, I get x is equal to plus or minus I root 3, which does not count as an inflection point, so it's only the point at x equals 0. And since 0 was one of the intercepts, or actually both of the intercepts, the inflection point is the coordinate 0, 0. So once you find the inflection point, you want to draw a number line and include the points that are not in the domain. And you take points within each interval and substitute them into the second derivative. And again, we're not looking for the value, but rather if this is positive or negative, so we know if it's concave up or concave down. So for the second derivative, you can write the numerator in factored form, 4x times x squared plus 3 over x squared minus 1 cubed. So when you take negative 2 and substitute it into each factored part, you'll have a negative times a positive over a positive, which it's negative, means that it's concave down. And then for negative 1/2, you'll have a negative times a positive over a negative, which is positive, which means that it will be concave up. And then for 1/2, you'll have a positive times a positive over a negative, which is negative, means that it will be concave down. And then for 2, you'll have a positive times a positive over a positive, which is positive, so your graph is concave up. So when we draw this graph, the first derivative told us that the graph was decreasing the entire way. But to the left of -1, it was concave down. Between -1 and 0, it was concave up, but still decreasing. And then concave down from 0 to 1, and again still decreasing. And then to the right of 1, the graph was decreasing but concave up. If we had drawn it in the quadrant below, it would have been increasing and concave down. So this graph is the final answer. For number 2, f of x equals 3x to the 4th plus 4x to the 3rd. So first we start with f of x, and the first thing we want to find is the domain. And since we don't have a fraction or a square root, the domain is all real numbers. So the next thing I find is the x-intercept, and the way I find the x-intercept is I set y equal to 0, and I factor the numerator, and I take x cubed, set it equal to 0, 3x plus 4, set it equal to 0, and I get x equals 0, and x equals -4/3. So to find the coordinates of the y coordinate that gets matched with each x is I take f of 0, I take 0 and substitute it into the original function to get 0. So one x-intercept is 0, 0. And then I take -4/3, and if I reduce this 81 to 27, I have 256 over 27 minus 4 times 64 is 256. So the points that are the intercepts are 0, 0 and -4/3, 0. Next, to find the y-intercept, I substitute 0 in for x, and I get 0. So the y-intercept is 0, 0. And the last four things, the vertical asymptote, the whole, the horizontal asymptote, and the slant asymptote, are all none because this function is not rational, meaning that it's not a fraction. You only check for the asymptotes in the whole when you have a rational function. So the only points that I'm going to put on this graph is the origin at 0, 0, and then negative 4/3 0 is right about here. And now I can move on and find everything that has to do with the first derivative. So the first derivative is 12x to the third plus 12x squared, and the domain of this derivative is all real numbers. So I start by finding the critical points. So I take 12x cubed plus 12x squared and set it equal to 0. So when I take 12x squared and x plus 1 and set them both equal to 0, I get x equals 0 and x equals negative 1. So since x is 0, that means one of the critical points is 0, 0, so I don't have to substitute that back into the function. But to find the y-coordinate that goes with negative 1, I take f of negative 1. So I have 3 times 1 plus 4 times negative 1. 3 minus 4 is equal to negative 1. So the other critical point is negative 1, negative 1. And if I take these 2 points and put them on the graph, these 2 points are going to be either maximum values or minimum values. And the way I'll determine which ones they'll be is I'll use the first derivative by picking points in between the intervals of negative 1 and 0. And I'll write the first derivative underneath. And you can also use the form 12x squared and then x plus 1. So if you take negative 2 and substitute it in to each group, you have a positive times a negative, which it's negative, so it will be decreasing. And then when you take negative 1/2, it will be a Then when you take negative 1/2, it will be a positive times a positive, which is positive, so the graph will be increasing. And then f prime of 1 will be a positive times a positive, which will be increasing. So the graph is decreasing to the left of negative 1, but increasing between negative 1 and 0, and then between 0 and infinity. So before we put this on the graph, let's find the second derivative and see if there are any inflection points. And the second derivative is 36x squared plus 24x And to find the inflection points, I set this equal to 0. And I factor out a 12x. And set each factor equal to 0. And I get x equals 0. And x equals negative 2/3. So now if I take points in each of these three intervals, and again, the equation of the second derivative in factored form is 12x times 3x plus 2. So a negative 1 times each group of parentheses is negative, which means that it will be positive, so it will be concave up. And then negative 1/2 will be a negative, times a positive, which will be negative and therefore concave down. And then 1 will be a positive times a positive, so it will be concave up. So to put this all together, the graph is decreasing to the left of negative 1, but increasing to the right of negative 1. And the graph is concave up to the left of negative 2/3 and to the right of 1. So to put this all together, the graph is decreasing to the left of negative 1 and increasing to the right of negative 1. And it is only concave down between negative 2/3 and 0. So when I connect these points, it is decreasing to the left of negative 1 and then increasing. But the origin is a critical point, so it has to have a horizontal tangent, and it is still increasing. But by the second derivative, the graph is concave up, then concave down, and then concave up. So this graph is a graph of the function 3x to the fourth plus 4x to the third.